In the next two chapters, we're going to be studying electricity. We're going to divide it into two parts. Chapter 22 deals with electrostatics. Anytime we hear the word static in physics, we know that means at rest. So we're going to be looking at electric charges that are at rest. Chapter 23 will deal with electric current, which is what you guys think of when you think of electricity. There's two types of electric charge, positive and negative. Benjamin Franklin was the first person to actually use those terms. He could have called them black and white charge or up and down charge, but he picked positive and negative, and that's worked really well for us. We know that if you have like charges, they will repel one another. So two positive charges will repel each other, or two negatively charged things will repel each other. If you have unlike charges, they attract. So a positive will attract a negative will attract a positive. That's an interaction. That force is always the same on both objects because of Newton's third law. One of the things we know is that all matter is made up of protons and electrons and neutrons, atoms. But most matter is electrically neutral. In other words, it has no net charge. If you were to add up all the positive charges and all the negative charges, it would add up to be zero. We also know that the electrical forces, they're responsible for all of the bonds in chemistry. Electrostatic forces are what hold the molecules in this sheet of paper together. They're what hold the molecules in your skin together. It holds this table together. All of the bonds in chemistry are due to electric charge and electrostatic forces. We also know that this electrostatic force is billions and billions of times stronger than gravitational forces. If one variation of electrostatic forces called electromagnetic forces is actually a magnet. And a magnet is stronger than gravity. If you think about it, just if you hold a magnet, it will pick up a bunch of thumbtacks that gravity's trying to pull down. So we know that that force is stronger than gravity. Now, having said that, most matter is neutral. So most of the time we don't observe electrostatic forces because they can, positive and negative charges can, quote, cancel each other out. Gravitational forces don't get canceled out. So even though they're much weaker, we see them really more often. Just a quick review of atoms. We did not cover the chapter in this textbook on atoms, but you should have learned enough about atoms in high school to be comfortable with this. We know that atoms are made up of three particles. They have protons, which are positively charged. They have neutrons, which have zero charge, and electrons, which are negatively charged. It's really just sort of an accident that electrons were considered negative and protons positive, because when Benjamin Franklin named positive charge and negative charge, we really didn't know enough about the structure of the atom yet. They hadn't discovered protons and electrons. If we draw a picture of an atom, it would have a nucleus, and inside this nucleus, you would have positively charged protons, as well as some zero charged neutrons. So I'll put 4 neutrons, and 4 protons. Now, like charges repel, so it would seem like the protons in the nucleus would repel each other and the nucleus of the atom would fly apart. But there is another force that's stronger than the electromagnetic force. It's called the strong nuclear force. That strong nuclear force is what holds these protons together inside the nucleus. Now, surrounding the nucleus are all of the electrons, and you've probably seen them drawn where they look like they're orbiting something like this, and I can draw some orbits. So there's an electron, and there's one electron. I'll put one on each orbit. And here's an electron, and here's an electron. But we don't really think of them being in orbit so much anymore. We think of them being in something called an electron cloud. So the nucleus is just surrounded by a cloud of electrons. But inside that electron cloud, there are still considered to be orbits. And some electrons will orbit very close to the nucleus. Those are called the inner orbits. And some will be on the very outer orbits, or the outer shell. They'll sometimes talk about a shell. The electrons that are on the very outside of the atom are often gained and lost. If there's only 1 or 2 in that outer shell, which is what happens with metals, metals have only 1 or 2 valence electrons, they'll often just let those electrons go. So they're called free electrons. We'll come back to that idea. Now, in other materials, non-metals, they hold on to all their electrons really tightly. We do know that the charge on an electron and a charge on a proton are the exact same size. They have an equal magnitude. We call that charge on an electron the elementary charge. And we represent it usually with a lowercase e. So if we're talking about electrons, electrons have a charge that's equal to negative e, and protons have a charge that equals positive e. So protons and electrons have the same size of charge. In most atoms, the number of protons and the number of electrons is exactly equal, and you have a neutral atom. Another way of saying neutral is to say that the net charge is 0. Net charge, remember when we talk about net force, it just means the total charge. So if the net charge, if you add up all the positives and all the negatives and you get 0, that's a net charge of 0. One more thing though about electrons and protons is their mass. The mass of a proton is approximately 1,800 times the mass of an electron. So in terms of mass, electrons are very, very small compared to protons. Most of the mass of an atom is in the nucleus. Those heavy particles we call protons and neutrons. Electrons are really light. The mass of a neutron is approximately the same as the mass of a proton, but they are actually a tiny bit heavier. So neutrons are heavier than protons, but not by much. A neutron is also about 18 times heavier or more massive than an electron. Okay, in physics, we have 4 major conservation laws, and we've already studied 2 of them. We've studied conservation of energy, We know that energy is never created or destroyed. It's only transformed from one form into another form. We've also studied conservation of momentum. If there are no external forces, no outside forces, the momentum of a system is constant. If we take the entire universe as our system and we count everything in the universe as part of our system, then the momentum of the entire universe is constant. Okay? This one, today we're going to talk about conservation of charge. And basically, conservation of charge simply says that charge cannot be created or destroyed. And that's really what conservation of charge says. You can't make charge and you can't destroy charge. It is an innate and intrinsic property of matter. I'm going to put a but on it. But you can transfer charge from one object to another. So, oftentimes, and it's always the electrons that we're transferring, the only way to get a proton out of an atom is to have a nuclear reaction because the protons are trapped inside the nucleus. So when we talk about transferring charge, we're really talking about moving electrons, those free, looser held electrons in the outer shell, from one object to another. Let's talk about two things that light combine. One is sodium, and one is chlorine. Sodium is a metal, and it happens to have one electron in its outer shell. It really doesn't like having just one electron in its outer shell. If you took chemistry, you probably know that atoms prefer to have a full shell on the outside. So if they just have one electron, they tend to get rid of it. So what happens with sodium is it transfers one of its electrons from here to here. That makes the sodium positively charged because now it has one more proton than electron. Instead of having equal numbers, if it gives away an electron, it's missing an electron. It'll be positively charged. That's called a positive ion, I-O-N. Chlorine, on the other hand, has 7 electrons in its outer shell, and the magic number is 8. It'd love to have 8, but it only has 7. So it happily accepts this extra electron. If it has one extra electron, it's going to be negatively charged. So this is a positive ion. It's missing one electron. This is a negative ion. It's gained one electron. Now, we know opposite charges attract. So what happens is these positive sodium ions attract this negative chlorine, and we end up with sodium chloride. You guys think of it as table salt. That's what sodium chloride is. But I just wanted to point out these electrostatic forces, this attraction between positive and negative is why we get salt. But also this idea that we can't destroy this electron, but we can move it from here to here, and we have conservation of charge. Another idea that we might want to think about is what happens if you just take a piece of fur. There's a piece of rabbit fur or something, and you take a piece of PVC pipe, just a little rod or something. This works really well. If you take the fur and you rub it on the PVC pipe, and if I had that'll come with me this summer, I could demonstrate that. What's going to happen is you're going to transfer electrons from the fur to the PVC pipe. When you get finished, let's suppose that this ends up with some charge I'm going to call positive Q. We use Q for electric charge a lot. If this ends up positive Q because it gave away some electrons, this is going to end up with a charge of negative Q because it gained those electrons. If the fur lost 1,000,000 electrons, then this PVC rod must have gained 1,000,000 of electrons. Can't create them, we can't destroy them, but we can move them. And as a result of moving electrons, things that used to be neutral can now be charged. Keep dropping my eraser, I'm sorry about that. Okay. Coulomb's law. Coulomb's law is the law that tells us how strong these electric forces are. What's the magnitude of this force? And it looks like this. It says the force is equal to K times Q1, Q2 over the distance squared. That should almost look familiar. It sure looks a lot like the law of universal gravitation. You'll remember when gravity was concerned, our constant was a capital G, mass 1, mass 2, over the distance squared. So Coulomb's law is an inverse square law, just like gravity. It behaves very similarly. However, let me point out some differences. K is equal to 9 times 10 to the 9th. Notice that's a fairly large positive exponent. G was equal to 6.67 times 10 to the negative 11. That's a fairly tiny negative exponent, or a large negative exponent, making a very, very small number. Okay? This alone is some evidence that gravitational forces are actually very weak. The only way to get rid of this, to have this be a big source, is for one of those masses to be really large. K, on the other hand, is a big number. We don't have to have huge charges to get a pretty big electrostatic attraction. The same thing happens with electrostatic forces that happened with gravity. If we double the distance, we end up with 1/4 of the force because this turns into 4d squared. So our new force, I'll call it F prime, is only going to be equal to the old force divided by 4. If this is the original force, if I just double that distance, if I come along and I triple that distance, the new force is going to be that original force divided by 9. I'll end up with 1/9. So it's an inverse square law. It behaves very much the same way that gravity behaves. Okay. If you double the distance, you get 1/4 the force. If you triple the distance, you get 1/9 of the force. If you make them 10 times apart, 10 squared is 100, you're going to get 1/100th of the original force. The other obvious difference between electrostatic forces and gravitational forces is gravitational forces are always attractive, and electrostatic forces can be attractive when you have opposite charges, but they are repulsive if you have like charges. All right, most materials are classified as either being a conductor that conducts electricity well or an insulator that does not conduct electricity well. The thing that makes a good conductor are loosely held outer electrons. So what has loosely held outer electrons? Metals. These are sometimes called free electrons. Any metal is a good conductor. Gold, silver, aluminum, copper. In fact, the more expensive metals like gold and silver and platinum are usually the very best conductors. However, they're really costly, so most wiring is done in copper. Insulators do not allow charge to flow easily. We think of things like rubber, glass, and the reason's really clear that these things are not good conductors. They have tightly held electrons. They just don't have any free electrons to donate. Metals have those 1 or 2 electrons in their outer shell, and they're happy to donate them and just give them away. There are some materials that don't fall into either one of these categories. Semiconductors fall in the middle. And the most common semiconductors that you've probably heard of are silicon, as in Silicon Valley, and germanium. And semiconductors are really interesting because they're not good conductors, but they're also not great insulators. And if you put just a little bit of impurities in them, you can make them conduct fairly well, and you can make them act like switches. So under the right circumstances, a silicon will allow charge to flow, and under the wrong situation, it doesn't allow charge to flow. And so it kind of acts like a switch that can turn on and off. Silicon diodes are used extensively in electronics, as well as other electronic things made from silicon. And our final category is what we call superconductors. And superconductors have virtually no resistance to electric current. They're not just easy for electric current, they're like super easy. They don't have any resistance at all. But there's a big catch. At very low temperatures. Most materials that become superconductors are only superconducting when they're at temperatures very, very close to absolute zero. Absolute zero is a negative 273 degrees Celsius. But scientists and researchers, they're working on creating superconductors that don't have to be quite as cold as the original ones. So they're working on trying to make it a more practical use. But eliminating electric resistance would be an energy-saving thing in the long run. Okay, let's go back and talk a little bit more about how we charge things and how we transfer charge. There's 2 basic methods. One is conduction. Another word for conduction would be direct contact. Now, conduction works really well and really easily if you have 2 conductors. If I have a metal sphere that has a charge of plus Q, I'm going to put it on some stand that's an insulating stand so the charge, so this is an insulator. It won't run off. It stays up there on this metal sphere. And I have another one just like it. And it doesn't have any charge. So this one's got a charge plus Q. This doesn't have any charge. If I pick this one up and I move it over here so that they touch, well, the charge is going to redistribute. Notice positive charges can't move, but electrons can. If this is a metal sphere, electrons from over here are going to go over here. Remember, this electrons are going to try to spread out. They're going to try to get close as they can. So this is going to attract only like that. And they're going to flow temporarily until the charges on those two spheres are equal. So if we wait just a minute, this one's going to have half the charge, and this one's going to have half the charge. They'll still both be positive, but they shared that charge. Anytime you bring two conductors in contact, they're going to share the charge. If they're both neutral, they'll both stay neutral. But if one's positive and the other's neutral, they're going to share that positive charge. Or if one's neutral and the other one's negative, they're going to share that negative charge. Okay, another way you get charging with direct contact is plain old friction. If it's wintertime and the air is dry, if you go scuffing your shoes along the carpet, you may reach up and touch the doorknob and get a shock. And that's because when you were scuffing the carpet, you were transferring some of the electrons from the carpet onto your shoes and onto your person. Same thing happens in the dryer. If you put your socks and your panties and all your laundry in the clothes dryer, it tumbles around together. You'll notice that when you take it out of the dryer, you've got all this static electricity. Well, you didn't create electricity in the dryer, but you did transfer some of the electrons from one item of clothing onto another item of clothing. But when you transfer those electrons from one item of clothing into another item, you created positively charged clothing items and negatively charged clothing items, and they stick together. So friction is often the force or use that causes charging by contact or charging by conduction. The other method is charging by induction. In induction, we don't actually touch the charged object, but we use it a lot. Suppose I have a bar of metal. Only that bar of metal is in two pieces, but they're stuck together. So as long as those two pieces of metal are sitting together, it acts like one piece of metal, and it's neutral. If I bring something positively charged close to it, so let's get a rod that's got some positively charged, it's got a bunch of, it's going to immediately attract electrons over here. And I do 1, 2, 3, 4, 5, 6, 7, 8, 9, so on, which is going to leave this chart, and really I should put them more like this. So I've got 10 little negatives over here. Well, it's going to make this side positively charged. We're going to draw electrons are going to be attracted to that. Okay, well what is, since these are not one piece, if I now separate them, this one's going to end up negative, and they're going to spread out because it's a conductor, and this one's going to end up positive. And I didn't count this time, but the number of positives and the number of negatives will be equal. I never actually touched the charged object to this block of, this kind of double block of metal. But when I did, you can see just by bringing it close, not touching it, we get what we call charge separation. So now if I separate the blocks while I've separated the charge, I end up with a negatively charged object and a positively charged object, all of which still supports conservation of charge. I didn't create or destroy any charges. Okay, so there's one other thing we need to look at about charge, and that's charge polarization. Neutral materials can be attracted to charged materials, and that doesn't seem to make sense at first. Why would a neutral object be attracted towards a positive or negatively charged object? It doesn't matter which. They're never repelled, they're always attracted. So what's going on with this neutral object that causes this attraction? Well, some atoms or molecules, or not atoms, some molecules are what we call polar molecules. One side of the molecule is a little bit positive and one side of the molecule is a little bit negative. Perfect example of a polar molecule is water. Water molecule looks like an oxygen, hydrogen, hydrogen. Probably should have just drawn it. Okay. Notice it's kind of a funny V-shaped molecule. It's an H2O. Well, what happens is there's some sharing going on of electrons in here and electrons in here, and this side of the molecule ends up being, I'll make sure I get this right. I could be wrong on this, but I'm going to say this side ends up being a little bit negative, and this side ends up being a little bit positive. There's a slim chance I got that backwards, but I think I'm right. But the point is, even though the whole molecule is a neutral molecule, it's kind of got a positive side to it and a negative side to it. Even things that don't have a negative and positive side to them, if you bring something charged close to them, they kind of do. So here's what happens. Suppose you have a comb, and you brush your hair with your comb a bunch of times. And when you get through brushing your hair with your comb a bunch of times, it ends up positively charged because it got rid of some of the electrons. So I have this comb, it's positively charged. And I bring it near some little bits and pieces of paper. And here's little bits and pieces of paper. And you go, well, these little bits and pieces of paper are actually neutral, but you'll find that you can take your comb and actually pick them up. They'll be attracted. And the reason is the molecules inside the paper, those polar molecules, the negative side of the molecule is attracted to the comb. So the negative side of the molecules ends up pointing this way, and the positive side of the molecules ends up pointing that way. Well, since the negative side is a little closer to the comb, it'll be attracted. Even though there's a repulsion between the positive side, there's an attraction to the negative side, and the negative side is a little bit closer, so it attracts that. So this charge polarization we're talking about is when these molecules line up so that all of the molecules have their negative side of the molecule on one side and the positive on the other side. Now, one of the things we know is that gravitational forces between masses act over distances. The masses do not have to be touching. And electrostatic forces also act over distances. The two charges are not actually touching. One of the ways that this has been explained is to think of the idea of every mass being surrounded by a gravitational field. The larger the mass, the bigger the gravitational field. So the Earth would have a very large gravitational field, but the cap to my marker would have a very small gravitational field. And when an object, another mass, it enters a gravitational field, there's a reaction between their fields. There's that attractive force. We can think the same thing about electric fields. If I think of an electric field, it would surround all of the charges in the universe. Let's suppose we have a fairly large positive charge. We would say there's a field surrounding it everywhere. And if you brought in another smaller charge, it's also positive. You know it would feel a force pushing it away. Or if I brought a little positive charge right here, it would feel a force pushing it away. And what we see is now if I bring in a positive charge anywhere close to this, it gets pushed away. And the closer it is, let's make it really close so the distance is small, the bigger force it feels. As it gets farther and farther away, it feels a weaker force. We can represent our electric field with electric field lines. This electric field would look like this. Now I can't draw in 3D, but you need to remember this would actually be in 3D. This is for a point charge. It would extend out in all directions, okay? The size of that electric field is given by this formula. It's the force the charge feels divided by the size of the charge. So if I put a little charge Q right there, the strength of the electric field right there is the force that this charge feels divided by the charge. Notice it's going to give us units of newtons per coulomb. So because we're taking force and we're dividing it by charge. Okay. It's really hard to visualize electric fields without these electric field lines, but an electric field will always point away from a positive charge because it's a vector field. It has direction. And in the direction, if this gives us the magnitude, the direction is the direction of force on a positive charge. So all I have to do to get the direction is I have to think, what direction would a positive charge? Notice if I had, this is positive. If I had a little negative charge, it would actually be attracted. Negative charges actually feel forces that are opposite the electric field. Positive charges feel force in the direction of the electric field. Now, electric fields point away from positive charges. If I change my picture, and I let this be a negative charge, well, a positive charge now is going to be attracted. So I'm going to have to go through and change all of my arrows to point toward the negative charge. That's a little different. Gravitational field wouldn't have two directions because it would always be attractive. The Earth's gravitational field always points towards the Earth because it attracts other masses. But electric fields, you have to know, they point away from positive charges, but electric fields point towards negative charges. Let's just do one more picture just because we can. Just to give you an idea of what electric fields might look like in other situations. If you had a situation where you had two plates and you had a positive plate over here and you had a negative plate over here, think about what the direction would be if you were a positive charge. Well, if I put a little plus in here, remember, it'll be pushed away from positive toward the negative. You can see in between here that the electric field should point like this, away from positive towards negative. That particular type of electric field is called a uniform electric field, and we're not even studying that in this class. But I do want you to see that it's really easy that electric fields always point away from positive. They always point towards negative. Electric potential energy. Well, think about masses. If I pick something up and I set it and I move it away from the Earth, I increase its gravitational potential energy. In fact, the farther I put it from the Earth, the more gravitational potential energy that it would have. Well, I kind of can do the same thing with charges, only in some cases, it's the closer together. It can be both with charge because we have both attractive and repulsive. But it might help if we think about a spring. If I have a spring and it's in its relaxed state, it's not compressed, it's just relaxed. If that's its equilibrium state, it doesn't have any potential energy. That's just its natural state. But if I come along and I push it so that it's compressed, it has more energy. It has just by me pushing against it. Remember, if I do work against gravity, I get gravitational potential energy. If I do work against the spring and I take my hand and I press that spring, it has elastic potential energy. If I let go, it'll go spring back out. If I put a mass here and let go, it can cause the mass to go sliding off that way if it's sitting on a table or something. But you can see that I've increased its potential energy. I can do the same thing with a charge. If I have a relatively large positive charge and I have a smaller one over here, that system has a certain amount of electric potential energy. But if I take that charge, pick it up with my finger, and I push against it and move it till it's closer, it's got more gravitational potential now because that repulsive force is greater. If I let go, those charges will go moving apart from one another if they're both free to move. They'll go moving apart because I've increased that electric potential energy. Now, we can talk about electric potential energy when we study electricity, but it's actually not what we talk about the most. Instead, we usually talk about something called the electric potential. Sometimes it's called the electric potential difference, and it's often called plain old voltage because electric potential is measured in volts. To calculate electric potential, we just do the electric potential energy divided by the charge. Well, electric potential is volts. If we look at the units, we find out that 1 volt is 1 What do we measure potential energy? We measure that in joules. Per, what do we measure charge in? Coulombs. I can't even remember, we've talked about the fact that when we measure charge, we're going to measure it in a unit called a coulomb. So 1 volt is 1 joule per coulomb of charge. I want to make sure you know what a coulomb of charge is. 1 coulomb of charge is equal to the charge on 6.25 times 10 to the 18th electrons or protons. It's a huge number. That is a trillion. Nope, I'm wrong. It's a billion. 10 to the 18th. 6.25 billion electrons is equal to 1 coulomb of charge. Okay. Electric potential, voltage, it tells you the electric potential energy per unit of charge. What does that really mean? Well, it means if you've got a 9-volt battery, it gives 9 joules of electric potential energy to every coulomb of charge that flows through it. How does the battery give 9 joules to every coulomb? Well, a 9-volt battery does 9 joules of work on the charge and gives it 9 joules of potential energy for each coulomb that flows through. If you have a 12-volt battery, it does 12 joules of work on each coulomb, and it gives it 12 joules of potential energy. In the next chapter, we're going to talk a lot more about voltage because we're going to talk about current electricity. But voltage is the thing that causes that push on that electric charge that allows electric current to flow. If we don't have a potential difference in electric potential, we're not going to have any electric current. The last section in this chapter deals with the idea of electric energy storage. The most common way that we can store electric energy to use later, we do it a lot, is with something called a capacitor. Capacitors are the most commonly used electric device, and it stores charge, positive and negative charges, which in a sense stores electric energy. Most capacitors look something like this. You have 2 plates, and you connect them to the terminals of the battery. That one there, that one there. When you connect them to a battery, charge will flow until these 2 plates reach the same voltage as the battery. We call the terminal voltage. One plate will be positive, it'll have a charge of plus Q. The other one has an equal charge of minus Q. Has to be equal because of conservation of charge. So essentially, if I take 10 electrons off this plate and bring them over to this plate, this will be plus 10 electrons, this will be minus 10 electrons worth of charge. If we were to increase the voltage, it would increase the amount of charge. That makes sense. If we make the plates larger, we can increase the amount of electric charge that's stored. And in doing so, we increase the amount of electric energy that's stored. So if I want to increase the capacitance, I really have three things. One, I can increase the voltage. I can't increase the capacitance per se. I can increase the voltage. I can make the plates larger, or I can bring the plates much closer together. All of those will allow more charge to be stored on the capacitor. Now, from a practical standpoint, almost since everything has capacitors, there has to be a really easy way to do this. So most capacitors are parallel plates, but those parallel plates look more like sheets of tinfoil, where you have a sheet of something like foil, and in between we're going to sandwich a piece of paper. See if I can draw this. So we've got, and we'll probably put another sheet of paper down here. Okay, so we've got metal, like foil, and then we have an insulator, like a piece of paper, another piece of metal, another piece of insulator. If I make a little sandwich out of my layers, I can roll them up like this. I will need one lead off of each piece of metal, so there'll be a lead here, and there'll be a lead here. But when I get done, this is what they look like. I'll have my two leads coming out. I can make a really large area capacitor, but then by rolling it up like a jelly roll or cinnamon roll, I can save a whole lot of space. Now, capacitors can store a lot of charge. If you see those warning labels on the back of electronic devices, do not open, warning high voltages, the big concern is that if you have a fully charged capacitor and you were to touch those ends together, you could get a sizable shock. Okay? Do need to be, generally when you're talking about capacitors, when they do let the charge flow, it's very brief, but they can contain a high level of electric charge. Okay. That's our discussion on electrostatics. I will put together the next video, and it's going to be about electric current.